to thank the organizers for a wonderful conference, an opportunity to speak here, and, well, an opportunity to be here in Rio, which is a great pleasure. Well, maybe before I start the talk, I would like to remind you that there will be a next conference, which is a kind of sister conference series of Poisson, which is called Higher Structures. And this year it will be in the Schrödinger Institute in Vienna. And here are the dates of the school and of the conference. And you can simply Google Higher Structures 2010 to get more information about the event. Well, so I'll be speaking about deformation quantization. And the Kashivara-Verne, or maybe I shorthand KV problem. And the goal of this talk is as follows. So there were already several talks where associators and the Grothendieck-Teichmüller group were mentioned. We would like to better understand the relation between associators and star products. Well, in fact, there is a work of Tomarkin which tells us that given an associator, we can build a formality morphism, and we can build eventually star products on Poisson manifolds. However, this construction is rather complicated. We want to make it a bit more concrete. And, well, I must say, I don't quite know how to make it more concrete in the general case. However, there is one case which seems to be quite interesting, where one can really make everything with concrete and rather precise formulas. So, what I know how to do is to look at the case of a manifold to be a dual of a Lie algebra. And in this case, fortunately for us, there is a classical problem in Lie theory, which is called the Kashivara-Verne problem. And it helps us understand this mysterious relation between associators and star products. So, in fact, even this story is quite long and involved. So, for the purpose of my talk, I devised the following way of presenting it, which is perhaps a little bit controversial. So, I'll start with a small map of some part of the associator universe. You know, so associators, that's a big field. So there are many things there, and I'll show you some of those things without much detail, and then we'll work out some paths in this associator universe, which would lead us from associators to star products in this particular case. And of course, on this path, I'll only give you like simple and nice facts, and all the complicated facts I'll kind of throw out, or maybe cheat when I need to present them. So, right. Let me try to draw some kind of part of the map of this associator story. The Greenfield associators form a set, and you already seen in the talk by Pavel Severa. Well, let me see which color is best. So associators are solutions of the pentagon equation. Let me just symbolically write it down this way. So it's some kind of complicated algebraic equation which involves 5 copies of the element phi. And okay, we'll come back to perhaps a bit more detailed study of it. And this set is acted by a group which is called the Grothendieck-Teichmüller group, So I use a slightly different notation from the one in the talk of Pavel because this group comes in two different versions, so I prefer another version of it. And this action is free and transitive, which means that the set of associators is basically the same thing as this group, just we don't know where to choose the unit. So whenever we choose a point here, we can identify the set of associators with this group. So I'll say a bit more about this group in a minute, but this is a kind of mysterious and interesting object. One can think that one of the big goals is to better understand this GRT group. Now, there is, here we can say, in Lie theory, so the theory of associators are related to many fields, and in particular to Lie theory. And one of the things in Lie theory that we can think about is a set of solutions of the Cauchy-Vara-Verne problem. Again, I'll make it more precise a bit later, of the KV problem. And it also comes equipped with a free and transitive action of the Cauchy-Vara-Verne group, while here, for whatever reason, there is an index 2 and some hat, but whatever. So this is a group which acts freely and transitively on the set of associators, and there is a map from associators to solutions of KV, and GRT injects inside this KV2 hat group. So both actions here are free and transitive. Maybe I should also say that there is an equation to describe this set, and many of you probably seen such equations before. So this equation is of the following type. It's phi FF is equal to FF. So this equation is a pentagon equation. And this equation sometimes is called the twist equation. So in fact, they form two terms of some kind of non-abelian complex. You can say that this equation says that phi is a kind of non-abelian coboundary of F. And this equation says that phi is a cocycle, also in some appropriate non-abelian sense. Now, what is important for us, there is a map from solutions of the KV conjecture to star products on G star. So we can say this is now in Poisson geometry. And eventually, what we will do today, we're going to follow this chain of maps from associators to solutions of the KV problem. Of course, I still need to tell you what this KV problem is, and then to star products on G star. Then, of course, you see eventually, since GRT acts on associators, GRT going to act on the star products in the image here. And I'll try to explain how it works. But before doing that, maybe I want to show you one more part of this associator universe, because, well, it's really, there are many things, but maybe one thing is still interesting for us. So this is in number theory. Well, here associators map to so-called generalized multiple zeta values. And, well, perhaps you remember from Pavel's talk that associators, these are noncommutative polynomials or noncommutative series in two variables. So those series, they have coefficients. And generalized multiple zeta values, these are those coefficients. So these are coefficients in front of particular monomials in terms of those x and y's. And what is interesting here, there is also, on the numbers theory side, there is also a group acting on the whole story. It's called DMR. And GRT also injects into DMR. So you see there is a kind of similar picture on the Lie theory side and on the numbers theory side. Now, perhaps before giving you more concrete details of the story, I would like to mention some interesting consequences of this picture and also some big or maybe not so big open problems which exist in this field. So maybe here remarks. So one remark is as follows. There is an important theorem due to Drinfeld which states that the set of associators is non-empty. So you already heard about this theorem in Chevera's talk. But now let's just formally follow the lines, right? You see, since the set of associators maps into solutions of this KV problem, whatever it is, it implies that the set of solutions of the KV problem is non-empty. And the KV problem was designed in the end of 70s by Kashiwara and Verne to better understand the Duflos theorem on the isomorphism between the center of the universal enveloping algebra and the ring of invariant polynomials. So, in fact, it implies the Duflos theorem. And, well, here one can agree or disagree, but I think that's probably up to date, the shortest and the most elegant proof of the Duflos theorem. So you, by now there are many different approaches, many different proofs of the Duflos theorem from different sides. Now this is really based on some classical, and after all, I mean, when you look at the proof of this statement in Drinfeld is not so difficult. So then this implies that solutions of KV exist, and this directly implies the Duflos theorem. I should mention that this is not the first proof of the KV conjecture. So the first proof was obtained by Eckhard Meinrenken and myself with a different technique. But so I think this is probably, who knows, maybe this is an optimal proof in this context. Well, maybe another thing that I want to mention, you know, here on this number theory side, well, there are those generalized multiple zeta values, and the simplest generalized multiple zeta values, which in general depend on the associator. These are just ordinary zeta values of even numbers. So up to some simple normalization, this is pi to some power times Bernoulli numbers. And the Bernoulli numbers, perhaps I remind you that they are obtained from this generating series. So Bn over n factorial x to the n from 0 to infinity. And this is exactly the function that you probably remember we have seen in Damian Kalak's talk. And that's the function which is used in the concrete construction of the Duflo map. So that's there is a concrete function in this isomorphism which is basically built of Bernoulli numbers. And these are the same Bernoulli numbers which appear here on the number theoretic side of the associator theory, and that's those Bernoulli numbers which then enter the construction of the Duflo map. Right. Perhaps one more thing, just to give you a kind of a bit more general perspective on what's going on, there is a number of conjectures related to this diagram. First of all, I should perhaps say that all the groups which participate in the diagram, these are exponentials of graded Lie algebras. So GRT is an exponential of GRT, DMR is an exponential of DMR, and KV2 hat is an exponential of small KV2 hat. And so here there are several conjectures about those Lie algebras. One of them is really a famous conjecture due to Deligne and Drinfeld. And this conjecture says that the GRT Lie algebra is actually a free Lie algebra with one generator in each odd degree starting from 3. So with generators sigma 3, sigma 5, sigma 7, and so on. In fact, you see GRT acts on associators, and then this means that it acts on the images, on those generalized multiple zeta values that one obtains here. In particular, it turns out that if you take a generator sigma to I plus 1 and act on the coefficient of an associator which corresponds to the odd zeta value. So you see this guy, for some particular associator constructed by Drinfeld, it would be just the ordinary odd zeta value, which is some transcendental number. But in general, now this thing would change if we organize a flow using this GRT action. And it turns out that those sigma 2i plus 1s, these are exactly the guys which move odd zeta values. So this is one conjecture about the structure of the GRT Lie algebra. I think it is verified for degree, I'm not sure, I think up to 19. So this is, as I said, all those Lie algebras are graded, so it's very tempting to make numerical computer experiments to verify various conjectures. And, well, here I think it was verified up to degree 19. So the other two conjectures are that DMR is isomorphic to GRT, and I think this is also verified up to degree 19. This was done by the same person, by Racinet. And on the Lie theory side, there is a conjecture that this Lie algebra KV2 hat is a one-dimensional center in degree 1 plus GRT. And this is verified for degree less or equal than 16, and this is due to Albert and Torosian. In fact, well, here there is an interesting story about this computation. So this is related to my work in this subject. So I was working on it with Charles Torosian, and we already had this picture, but we had no idea what this KV2 hat group or what this KV2 hat algebra would be. And my hope was that it was just one-dimensional. I was convinced that it was just one-dimensional. So I have a bright graduate student, Masha Podkopayeva, who is here, and she did a numerical experiment and verified a somewhat different statement. There, up to degree 7, there was really nothing, because we were looking at some kind of commutator Lie algebra of GRT. So there would be nothing up to degree 7. So we had something in degree 1 and then really nothing up to degree 7. So I was convinced that my conjecture was true. But then Charles-Torreson said, oh no, like 7 is a very small number. Well, I mean, here it's a matter of your judgment. Is it a small number or a big number? And they set up a computer program together with his friend, Luc Albert. So it turned out that the standard software is used in Lie theory is not good enough to do the Kashevara-Verne problem. So one had to create some new software for that. And then in degree 8, they found something. So at first I thought it was a mistake. But then they also found something in degree 10 and degree 11, and it became apparent that it's just not true. And then again, the credit should go to Charles-Torreson. So he computed some first dimensions with this computer program, and then we had some graded dimensions for this KV2 hat Lie algebra, and he just ran through the list of graded Lie algebras known to the mankind, and it turned out to match with this GRT, and then we were able to prove that actually there is an injection from GRT to KV2 hat. So this result is due to Torreson and myself. Okay. So so much about the this general story. Let me now tell you a little bit about the Kashevara-Verne problem. So what it is and how it helps us understand the relation between associators and star products. Maybe the last thing I should say, I told you in the beginning that there is a general Tamarkin story, how associators give rise to star products. And I also told you that I want to explain it in some particular case of the space equal to G star. In fact, we don't know whether this is the same as a Tamarkin story. In all probability, it is, because it's difficult to imagine two stories which goes completely parallel, one in a general case, one in a particular case, and all the same words, all the same arrows. But actually, we don't know. Probably it is. Okay. So the Kashevara-Verne problem is a problem in Lie theory. And, well, let me just define some notation. Well, I will denote by Lie2 the free Lie algebra with two generators, x and y. And let me just say that it's a degree-completed version, so you can also consider infinite series. And prominently, there is a Campbell-Hausdorff series, which is an element here. So this is logarithm of ex, ey. And, well, as we know, it starts as x plus y plus 1/2 of the bracket of xy, and then there are some multi-brackets. So the Kashevara-Verne problem is as follows. We are asked to find an automorphism of this free Lie algebra which satisfies three properties. So first of all, it maps generators to their conjugates. So here you can imagine that this is an adjoint action of some exponential of a Lie series, this G. And f of y is equal hxy y hxy minus 1. So in fact, this form, it will be essential for the relation to the Duflo formula. The second property is that the sum of x and y is mapped to the Campbell-Hausdorff series. So you see, this is a kind of noncommutative change of variables which maps sum, or if you want to think of f inverse, it maps the Campbell-Hausdorff series back to the sum of your two basic variables. And then the third condition, at the moment I don't want to make it too precise. Let me put it in this way, condition on Jacobian of f. So in fact I'll tell you something about this condition later in some equivalent formulation, but in this non-commutative context there is a nice notion of Jacobian, it turns out. So this is a whole separate theory, and one imposes a condition on the Jacobian of this non-commutative change of variables. We'll see something about it a bit later in the talk. So now, well, unfortunately, I have to start erasing this big scheme of things. But so the last moment to say it. So now I'll tell you something about this arrow from associators to solutions of the KV conjecture. In fact, it's given by an explicit formula. And also then I'll tell you something about why those associators and why this pentagon equation, why does it intervene. So some natural reasons for thinking of the pentagon equation. Okay. Sorry? With? What? What do you mean? Yes, that's right. So? No, I mean, on the left-hand side you have x plus y, which is indeed commutative on the exchange of x and y, and you also have f, right? And f, maybe f is not, you see f can do something to x, but then something entirely different to y. So the right-hand side doesn't need to be symmetric on the exchange of x and y. So up to now it's okay. Right. So, sorry? Yeah, there will be a twist equation in a second, right? Okay, maybe in like 2 minutes. So first of all, maybe I should cite a theorem. So this is due to Benjamin Enriquez, Charles Torosian, and myself. And it says the following. Suppose that phi is a Drinfeld associator. Let me recall that phi is a kind of non-commutative series, a function of non-commutative function in two variables.
Anton,
yeah?
Could I ask the same question that Sergey just asked?
Yeah, sure.
Why is f of x plus y not equal to f of y plus x?
No, but f of x plus y is equal to f of y plus x. Absolutely. But f, right, it does something to x, and it does something else to y, right? So these are two elements of a free Lie algebra. No. But you see, I mean, I do what I want with x and with y, right? With some constraint. So these are maybe you shouldn't think of x and y as two arbitrary elements of some Lie algebra yet, right? So these are two generators of a free Lie algebra, and I do different things to them by this map. So this is an automorphism of a free Lie algebra. This means I should just say what happens to generators. Yeah, let's say suppose we have an example. It doesn't satisfy our conditions, but let's say f of x is equal to 0 and f of y is equal to bracket of xy, right? No, but I mean, like this doesn't satisfy at all our conditions, but this is an automorphism of a free Lie algebra. Yes, right. But it's as I say, it doesn't satisfy this condition, but it's an automorphism of a free Lie algebra. Then f of x plus y will be a bracket of xy. You see the left-hand side is symmetric. I mean, the starting point is symmetric, but this is skew-symmetric on the exchange of x and y. But because you have an f, and this f, it does what it wants, right? It's a free object, so it sets the rules. It can map it to symmetric or skew-symmetric or whatever, can completely mix up. Is it okay? Yeah, sorry, I think it's not. Right. Sorry for the confusion. Is it better now? Okay. So then you see this f is defined by two elements, g and h. So then g equal to one function of the associator, and h equal to some other function of the associator gives you an explicit solution of this KV problem. I must say that those very nice looking simple formulas, they were invented independently by Damian Kalak and Dmitry Boyarchenko. And in fact, they showed that they satisfy the second equation, the equation that you were asking about. And this mysterious equation, which I didn't write explicitly yet, that was our result. That we proved that actually they satisfy other conditions. So the story goes as follows. So Damian told us about his formulas. But the Boyarchenko formulas, well, we found them maybe by accident. So we were searching internet on some words. And it turned out that Boyarchenko had some hidden link on his home page. So actually, it's not posted. He has some kind of secret text on his home page that we were able to dig using, and so he had the formulas in the text. But well, now I think we acknowledge his contribution, although he tried hard not to make it public. Right. Right. So now, what is nice about those Kalak-Boyarchenko formulas is that they are completely explicit. You see, so given an associator, you have this solution of the KV conjecture, and the formula which relates it to a star product also going to be completely explicit. But maybe now I want to spend some time just explaining a little bit why there is this theory of associators coming into the game. And my starting point will be the Campbell-Hausdorff series. So in principle, associators could have been invented, well, perhaps by Campbell and Hausdorff, or if not, by Kashivara and Verne. So how should one proceed to do it? Well, let me, instead of two independent generators, take three generators, x, y, and z. And that's the analog of the Lie algebra Lie2. Now it will be a free Lie algebra with three generators. Now, let me take a sum of three generators, x plus y plus z. And let me do the following. Since this is a free Lie algebra, I can treat x plus y, let me say it in a vague way. I can treat x plus y as one independent generator and z as another independent generator. In this way, I get a morphism into a free Lie algebra with two generators. Now, I can apply the Kashivara-Verne map F in this free Lie algebra with two generators to obtain the Campbell-Hausdorff series of x plus y. This is my first generator, and this is z. So this guy, let me call it F1 to 3. And vaguely speaking, this means that I treat the first two arguments as a sum of them. And technically speaking, this means that I should conjugate x and y by some g, where instead of x I put x plus y, and instead of y I put z. You see, so on these two generators, this is like a linear automorphism with some g, which here I have x plus y, and here I have z instead of those variables, and here I can use it either for x or for y. So this would clearly give this effect on the sum of x plus y plus z. But then I can proceed and I can apply an automorphism which doesn't touch the element, the third variable, and which would give me, which would replace the sum of x plus y by the Campbell-Hausdorff series of x and y. And here, well, I just denoted by F12, but that's the guy which operates on x and y as I prescribe here, and it doesn't touch z. But you know, one nice thing that we know about the Campbell-Hausdorff series, this is it defines an associative product. So this means that Campbell-Hausdorff of CHXYZ is the same as CH of x, CHYZ. But now we can go back. Here it will be F23 minus 1. So transform y and z, don't touch x. And this will go to x, y plus z. And then we can go back here by now treating y plus z as one variable and x as the other one. So let me denote it by F1 to 3 minus 1. So you see, we made in a loop, and we return to the same expression. Let me introduce a notation. Let me call phi the composition of all those maps. So F1 to 3 minus 1, F2 3 minus 1, F1 2, F1 2 3. So, well, what do we know about it? We know that phi of x plus y plus z is equal to x plus y plus z. But of course, it doesn't mean that this phi is equal to 1, right? It just transforms this one element into itself. But otherwise, this might still be a non-trivial automorphism. And it's easy to verify that it satisfies the Pentagon equation. You know, I don't want to write the Pentagon equation explicitly, but you can imagine that now you can take 4 variables, and so this already looks like some kind of noncommutative co-boundary. So there will be a similar cocycle condition now of 5 terms. So basically, you need to make sure that when you substitute it here, all the f's would cancel out. And the thing that one still has to use, this condition, because there are some of the f's that you cannot move through each other unless this condition is satisfied. So that would be the way to discover the Pentagon equation and associators if one just thinks about the Campbell-Hausdorff formula. So basically, you know, associators, it refers to associativity. Associativity of what? Associativity of many things, but in particular here, associativity of the Campbell-Hausdorff formula. Right. Okay. Perhaps now it's time to speak about star products. So I promised that there will be star products in the game. Right. So star products on G star. So let me do it in the following way. In some minutes, I'll describe a map which maps this element f from the Kashigara-Verne story into some other element, let me call it f hat h. And this will be an endomorphism of the product of two copies of polynomials on G star and over formal power series in H. In fact, let's say we're gonna define those star products for polynomial algebras, and that would be the simplest thing. So this will be some kind of universal map. So here G is an arbitrary Lie algebra, let's say finite dimensional over a field of characteristic 0, and so this formula would give some kind of universal map. It only depends on the Lie bracket. It doesn't use any other structures. So I'll describe this map in a second, but maybe even before doing that, I want to show you how the star product will be constructed and how we get again the pentagon equation in this construction. So let me denote by M0 just the ordinary product map. So this is just a product of polynomials on G star. So then the star product MH will be simply given by formula a composition of M0 with FH hat. So you see, this resembles what we've seen like from the very beginning of the theory of star products. This is a kind of Moyal type formula for linear Poisson brackets. So we know that there is such a formula, just the classical Moyal formula for constant Poisson brackets. And this is the Moyal type formula for linear Poisson brackets. You see, I kind of, fortunately or unfortunately, it takes this whole big theory to come to it. And I don't know whether there is a similar story in the general case, but who knows? Maybe that's the way. Maybe that's the way to approach it. So let me do the following. I want to show you another computation of the same type, but now on the star product side. Instead of writing formulas, let me draw pictures. So we want MH to be an associative product, right? Since we want to discuss associators, and let me draw the following picture for that. So the associativity of MH is a diagrammatic equality of the following type, right? So you have three inputs, one output, and you either first multiply the first two and then multiply with the third, or you first multiply second and third, and then you multiply with the first, right? So that's the associativity of MH. Well, let's substitute this formula also graphically into this equality. So, well, here on top we have M0. Then it is followed by this guy. Maybe I don't, to save space, I don't write FH hat there. And so then you have another M0. And here you have another F hat. So here I just substituted the Moyal type formula. It turns out that at least in this case, there is a way to push this F through the second M0, which gives us the following diagram. So you get M0. Here you get another M0. And if you succeed in pushing it through, there is a big guy, which we call F123. And then here there is a smaller guy, which we can call, if you want, F12. You see? So once we pushed it through, we can denote it by a different letter. And in a similar fashion here, there will be a similar picture. So here there will be F1, 2, 3, F2, 3, and then it goes down. So you see on top here, we have some object which is the same on the left and on the right picture, because this is just a triple product. So this is the product M0, it's just a product of polynomials. It's also associative, right? So this is, you can call it M03. And the ratio of these two sides, it is this phi converted into whatever, phi hat, right? So what we get from here is the following. So we get, if you want an associative product here, we need M03 to be stable under phi hat, where phi is a ratio of those Moyal operators. You see, it doesn't need to be 1. Maybe it's not 1. That's the room where associators enter. Because the first natural condition you might impose is to say that this ratio should be really 1 in order to assure associativity. But that's too strong, because then it turns out it would be correct in the case of constant Poisson brackets. But here, if you want to do this type of Moyal calculation already for linear Poisson brackets, it's too restrictive. And so that's the equation you get. And actually, that's the universal form of this equation. These are equations 2 and 3. So you see, I didn't erase this Kashivar-Verne problem. In fact, this third equation, I mean, I don't want to write it explicitly, but it is. So these two equations are equivalent to this equation star here. Okay, so in some way, that's also interesting. We study in some kind of automorphisms which universally stabilize multiple products. For instance, here we have a triple product, and we have to stabilize it in a universal way. So that's where those associators come in. So maybe now it's a high time to show you how this F defines this F hat. And I must say that here that's perhaps one place where I want to, well, if not cheat, but, well, you know. So this is, again, a very explicit formula. But if one writes it honestly, it will be a painful formula. So instead of doing it, let me say the following. First of all, given an F, I define another automorphism FH, which depends on the deformation parameter. And this is very simple. I just rescale all the arguments. Right, and here Y maps to H of H bar X, H bar Y, Y, H of H bar X, H bar Y, minus 1. Well, but now let me describe it in geometric terms. Right up to now we were basically doing algebra, but let me describe it in geometric terms because it's easier. For that, let's assume that our field was R. And in this case, well, now let's imagine that X and Y, instead of being in a free Lie algebra, are just elements of our concrete Lie algebra G. In this case, those formulas here, they define a formal diffeomorphism on the product of G cross G. So this is a formal diffeomorphism on G cross G. Now the space that we are interested in, SG tensor SG, it's actually the same as distributions on G cross G with a support at the origin. Right? So there is a natural isomorphism between these two spaces, and even algebraically we can make an isomorphism. But for us, it's sufficient to think that this is just. Now, what is f hat h? Well, first of all, we take fh and we take the corresponding push-forward map in distributions. So these are distributions here which are supported at the origin, so everything is compact. So there will be an operator, and we combine it with a multiplication by the Jacobian of fh. So this is for some technical reasons, because we act on distributions. We have to correct by the Jacobian. So now Jacobian of fh just with respect to the normal Lebesgue measure on G cross G. Right? It has a Jacobian, and now you see it's not, one doesn't need to think about any kind of tricky non-commutative Jacobian. Here this Jacobian turns out to be just a normal Jacobian of this map. So now maybe one should note some interesting properties of this construction. So one property is that this f hat h, when restricted on invariant polynomials, is simply equal to 1. And this is essentially because of this property 1. You see, it was a bit mysterious why we wanted to preserve generators, why we wanted to conjugate them. But that's because of this. Because we conjugate generators, nothing happens if our polynomials are invariant. And if nothing happens, then this operator has all the chances to be equal to 1. So it's designed in such a way. So that's basically was the idea of Kashivara and Verne, to design operators which don't touch invariant polynomials. And the second property is as follows. So now we have SG, and we have a family of products. So we have a star product there. And let's put, here actually we can just put h equal to 1 if you want. So what is this SG together with a product of M1? And, well, common sense tells us that it must be isomorphic to the enveloping algebra of G. And this turns out to be the case. So now you see on the side of the enveloping algebra, the G invariant part, this becomes the center. The G invariant part of U of G is the center. Now, this Moyal transformation, it doesn't do anything to the product of invariant parts. And therefore, the Duflos theorem holds true. So this is just to go back to Duflos to tell you why it works there. Well, there is one natural question in this context, and I don't really know what's the answer. So you see, as promised, we started with associators, and we found a completely explicit formula for a star product in terms of associator. And moreover, this is a nice star product. It verifies the Duflos theorem. So the question is, can one do the same for arbitrary Poisson structure? Well, I don't really know whether that's the way to do it, but at least it's kind of interesting, right? It's this old idea of Moyal type product, and here it basically gives you a solution. But well, I don't know. Maybe that's also the way in general case, or maybe there it's all completely different. Let me use the last 5 minutes to tell you something about the GRT action. So remember, there was this mysterious Lie algebra GRT. So Right. First of all, let me write part of a definition of it. So in fact, you can think of GRT elements as elements of Lie2. So Lie series in two variables, where psi of xy is equal to minus psi of yx. There is an equation psi xy plus psi yz plus yzx equal to 0 for z equal to minus x minus y. And there is the most complicated pentagon identity, but this one I don't want to write down. So an example of a GRT element, for instance, is this guy sigma 3. Remember, it's supposed to have generators in all odd degrees. And it's easy to see that already for the first equation, there is only one solution up to constants in degree 3. Because you have bracket x, xy, and it should be skew symmetric on the exchange of x and y. So you have to subtract y, yx. Right? So we actually know what sigma 3 is. Well, then one can see that it satisfies the other equations. So now the question is, what happens to the star product if we act by this GRT? So what happens to MH? And in fact, the answer was in the context of Tamarkin's approach. It was suggested by Kontsevich, and in this approach, we verified that exactly the Kontsevich formula holds true. In fact, the action of sigma to I plus 1 is given by an equivalence on star products. So it gives rise to equivalence of star product. And, well, equivalence of star product, this means that you need to have an operator acting on one copy of SG, right? And what is this operator in this case? Right? Again, let me identify SG with distributions on G supported at the origin, because otherwise, for me, it would take too much time to introduce algebraic notation. So then this guy maps to the multiplication operator of adjoint x to the power 2i plus 1. So this is a smooth function on G, and you can multiply distributions. You can multiply distributions by this smooth function. So, and it gives you a derivation, a derivative of the equivalence of the star products, which you get in this case. Now, it turns out that the action on those star products of GRT bracket GRT, it just goes to 0. So these are only those sigmas which act, and all their brackets, they act on the star product by 0. Note that the action of GRT on Fs, on these Moyal operators, is free. Right? So here GRT, full GRT acts. Now, when you compose, at least in the case of linear star products, when you compose with M0, it basically all dies with the exception of the generators sigma 2i plus 1. Now, maybe the last thing that I should say, if you want to see the action of other generators, or the action of a commutator of GRT with itself, of course, one way would be to go to star products on some more complicated nature, maybe not linear ones, but that we don't know how to do. But there is one very promising problem in harmonic analysis, or you can say in Lie theory. So there is an analog of Cauchy-Verne or Duflo story for symmetric spaces. It was already mentioned by Damien Clark in his talk. And in this case, it turns out that maybe one can see the action of GRT bracket GRT. Let me write just the last formula that I'm currently quite excited about. So there, in this case, we computed the action of the bracket of sigma 3 and sigma 5. And there, it turns out that, first of all, it's no longer an equivalence of stars. There, this is something which depends on two variables and doesn't want to factorize. And let me write it down. So this is now a function of two variables. Maybe I should write it more carefully. Adjoint x squared, adjoint y, adjoint x fourth, adjoint y, plus so on. You see, this is a trace of a commutator of two operators. So normally it should be equal to 0. But fortunately, in the theory of symmetric spaces, so the Lie algebra can be split right into the +1 and -1 subspaces of the involution. Here you see one takes a trace over the whole Lie algebra, G. But in this theory of symmetric spaces, one often has traces either or +1 or -1 part. And it turns out that if you take a trace only over one of those subspaces, then traces of commutators no longer vanish because you only take some partial trace. And so universally this is not equal to 0. This means that we probably see the action of higher brackets there. We don't know whether we're going to see the action of all of them, or of course, the hope would be that maybe then the action of GRT will be again free, or the GRT would inject, similar to how it works here. But this I cannot say. Of course, sorry. This is probably this is a bit messy what I wrote here, but it just indicates that there is life beyond Duflo theorem. So there are some interesting things. Okay, thank you.